Welcome to RadioViews. My name is Thalia Traianou and I'm a postdoctoral researcher at the VLBI group of the Max Planck Institute for Radio Astronomy. In this video series, we discuss with fellow astronomers about their latest science projects. Today, Dr. Jae-Young Kim is going to talk about a unique blazar. Enjoy!
Hi, so today I'm going to talk to you about my recently published paper, which is about the archetypal blazar object 3C279. Supermassive black holes are quite ubiquitous in the universe. You can find them almost in all galaxies. And when matter accretes towards the center of these galaxies, towards the supermassive black holes, they first of all shine very brightly, but also they can sometimes launch very collimated, strong beams of relativistic plasma outside. And these plasmas sometimes interact with the surrounding medium and can control the evolution of the galaxies. So it's considered that the evolution of the roles of these supermassive black holes play pivotal roles in the evolution of the galaxies, and therefore they are a very fundamental object to study in modern astronomy. So 3C279 is a very intriguing object and has been studied and observed over the last decade. For instance, it showed the first evidence of superluminal motions in the outflow, and also since the early days of gamma ray astronomy, we knew that this source was the brightest and often the most variable gamma ray emitter in the sky. But it was unclear how actually the source can be variable even on 5-minute timescales, for instance. And that requires the presence of a very compact emission region in the jet, which requires further investigation by interferometric techniques. So in 2013, our group already observed the target with a pre-ALMA EHT array to see if the source contains such a very compact emission region. And we found that actually such a region is present in the outflow. And in 2017, we added ALMA to the EHT array and made a first attempt to make the finest image of the source at 20 microarc second angular resolution. This is our new image. So as you can see, on lower angular resolution and on large scale, you can see a self-similar and somewhat boring jet structure that is pretty straight. But if you go to 1 millimeter and at the highest angular resolution, you can see a peculiar nuclear structure which is not noted by the lower resolution images. And that can be interpreted in very interesting ways. For instance, there can be either broad accretion disk, magnetic reconnection of plasmas, or shock waves, instabilities propagating through the jet outflows. But we found after testing with the observed the data that the most probable explanation is a large-scale bending of the outflow near the launching of the jet. And we also, by using the brightness and the compactness of this radio emission, constrained the internal properties of the plasma at the unprecedented scales that was inaccessible by the previous observations. So we learned a lot about the macro and the micro physics of this source, but if you want to know a lot of details and many other interesting results that I couldn't talk here, please check the link here, and that's it. Thank you.